Today I want to talk about state machines. I saw a talk recently where someone referenced to them, and in the chat around the talk people weren't completely sure what they were, and I remembered pairing with Mike Dickens once, and he suggested using a state machine. I'd never come across them. He introduced them to me. I thought they were incredible. I wondered, can I explain them? Can I help other people get that moment where they have another option of a way to work? A state machine is a thing which transitions between states. So it represents something about the system, and it has defined transitions between them. It might actually be easier to look at an example before talking about them. A switch is a really simple example of a state machine. It has the state on, it has the state off, and it only has one transition. It just toggles between them. A dimmer switch might be an example of an infinite state machine. It can hold any position between on and off. Here we have a finite number of states, on and off. They toggle between them. So it's a thing which is only in one state at any given time. In response to the input, it can transition between states. And once you know to look for them, you see them hidden inside lots of systems. That doesn't mean you have to write code that is a state machine. If you never do, you might be missing a trick, but you could just model the system that way. Your documentation might talk about the state machine, and it might explain why you didn't write code that way, but it's there. You can have a bigger example of an elevator that has an up and a down transition, and the transitions aren't valid in every state. So on the ground floor, on the lowest floor, you can't transition down. On the highest floor that the elevator will visit, you can't transition up. And a more complicated example might be a user account. You start anonymous, you fail to register, you remain anonymous. If you register successfully, then you're logged out. When you're logged out, if you fail to log in, you stay logged out. If you keep failing, you might be locked. Eventually your account might be disabled. There might be different transitions to get from a locked account to a disabled account. A locked account, often a time-based unlock. If you were locked more than 5 minutes ago, you're not unlocked. You're not locked anymore. Whereas if your account's disabled, you have to change your password. If you successfully log in, you become logged in, and from that state, you might change your password or log out. You can see how you could represent this as text in a repo, generate the images for your documentation. And so I thought I'd write some code to show what that looks like. The first decision is how to test them. Let's prove I can run tests. So I actually made a fake user pool. It has some results: registration succeeded or failed, logins successful or failed, login, how do you spell succeeded or failed. You can log in. There's a magic password that lets you log in. You can register. There's a magic username that means you can't register. There are tests to prove that works. So I could write a test where I say, some result is user pool. I think that was how So I've got a pool, and I can say some result equals pool.login something and stuff, and then use that result. And we could do that, and then eventually we'd refactor, and we would push that information into our state machine. So we'd have a state machine, and it would have some method, and in there we would have access to our pool, and we'd say pool.login, and we'd use the result in there. And it doesn't have to be a fake. This could be a mock. So, pool dot some method would equal mock, and would have a return value. right. Does that return value like that? Yeah. And we could use the mock, so you don't have to have that hand roll fake, you can use the mock. In all of those, actually, the only interesting bit is these results. Registration succeeded, registration failed, login succeeded, and login failed. I like Kevin Rutherford's definition of tell don't ask, which is tell me what I need to know, don't make me ask. So in this instance, we're making the state machine ask the user pool, whereas we could just tell it what it needs to know. What would that look like? So if we say test that registration failed leaves user anonymous, then oops, we can get rid of all of this, and we'll make a decision that this is going to be a polymorphic state machine. What does that mean? Well, it means that the type of the instance will determine the state. So we have a state machine, and it's going to transition. We'll use that language because that's what's in the documentation in the README. The transition based on some event. We've said we're going to look at the events, and so if is instance event, and what did we have? Login succeeded for sake of argument. Then let's have in here, we're going to start off anonymous, state equals anonymous, and does that need to be imported? No, it needs to be spelled correctly, and then it needs to be imported. Then state equals logged in, and we can keep going. Else if is instance event login failed, and so on. So I'm learning to write Python because I'm working with a team that writes Python, so I'm just going to Google what else if looks like in Python. Elif, obsession with then, you know, the state is anonymous, and so on. We'd end up with, for you know, multiple branches of an if condition, and in this if condition you could test, well, actually, you know, the only time we should see login failed, if we look at our README, we should see login failed. Well, we can fail to log in when we're logged out, and actually that's or when we're locked. So in here we could say if you know, if state is logged out, or state is locked, then, you know, whatever it might be. So that's not a polymorphic state machine. That's a state machine that we're mutating something about the state machine that we could test for. We could see what the state is after a set of things has happened, and that's perfectly valid. So, you know, that would work. Your test would pass. Your system would work. If these branches are small, that might even be something we'd keep forever. Often the branches aren't small. Stuff starts to matter in here. If we were, when we got to the point where we were modelling whether a failed login should mean we're locked out, then we're adding state, and that state should only be read on particular lines of code. So we don't, you know, failed login count, it would start as 0. Now, there's nothing stopping someone in the future coming in here and saying, oh well, failed, let's increment the failed login count, because they've misunderstood. Maybe you can't do that in Python. Self.failed login count. And that should be impossible, but it's not impossible in this code. It's possible, and we should seek to make the impossible unrepresentable in our code. So a polymorphic state machine where we use the types, the type of the state machine lets us do that. So what would that look like? Well, we can say, we can assert that the instance, our end state, is anonymous. That's what our test is telling us. How do we get to there? Well, the end state is going to be made by the state machine transition handling registration failed. And we don't have a state machine. Let's make one. State machine equals anonymous. Let's see. That should fail because anonymous doesn't exist. Let's create it. Now it should fail because transition doesn't exist, and it does, except I can't spell transition. Yep, super. Let's create that method, and it takes an event. And we're not doing anything, so let's be really lazy and return self. That's not how you type it, self. That should pass. So far so good. Let's test that registration succeeded leaves user logged out. We're going to have a really similar test. I'll start from the top because in fact I'm going to copy it. We're all supposed to pretend that we don't do copy and paste when we all copy and paste. We're not supposed to avoid it. We're supposed to feel guilty when we do it. We're supposed to feel the signal that we get from the system that we're copying and pasting. It's telling us we're missing something. So we're going to end logged out, and we're going to end logged out when registration succeeded. We can import that. Logged out isn't defined, so we can create that class. It should fail now because anonymous isn't logged out. And we can say, well, when we're anonymous, if the event is registration succeeded, then we're going to return logged out. Otherwise, we're going to return self. And logged out is not. We're going to return an instance of logged out. So now we can test. Well, we're logged out. Let's test that a successful login leaves user logged in. We can assert that the end state is logged in. We can get to the end state by saying state machine.transition through what? Through, well, login succeeded. We start our state machine. Well, we can cheat. We can say logged out. That might not look like cheating. Let's make this pass. So we need a logged in. Logged out doesn't have a transition. Let's give it one. Def transition takes an event. If is instance event logged in, then return no. Login succeeded, then we're going to return an instance of logged in, else we're going to return self. And that means now if someone makes a mistake and they pass a registration attempt to a logged out user, it just gets ignored. That's quite safe, but on the surface of it, it might not be right. So you might want to do something else here other than return self. There might be a subset of events where you return self, otherwise you return some error state, or throw an exception, let someone else handle the fact that something wrong has happened. I called this cheating. It's not really. When you have a logged out state machine and it transitions as a result of a login succeeded, then you have a logged in state machine. That's true, but it doesn't really give us the full story. The full story is that when you start anonymous, and we'll let it mutate for now, state machine equals state machine dot transition registration succeeded, and then you transition through login succeeded, you end up logged in. Why do I prefer that? Well, I prefer it because what we can do at this point is we can see a pattern. We're going to start with an anonymous user. We're going to receive and as a result transition several events, and then we're going to check what type of object we have at the end. And actually that means I can make all of these tests identical regardless of the number of events that are handled by the user. Let's do that. So we can have assert user transitions. What we're going to take, we're going to take events, and we're going to take a final state. And inside of here, we're going to say that the state machine is an anonymous, and we're going to say for each of the events, the state machine is the result of handling that event. And then we're going to say self.assert is instance, state machine, whoops, and final state, which means I can replace this test here with self.assert user transitions, and I can give it an array of anonymous, no, registration succeeded, and then login succeeded, and it will end up logged in. Okay, so quite a bit of code in one go. I think that will pass. It does. Can it fail? Brilliant. Should pass again. Yes. Let's stick that down. Let's stick that down out of the way. Yeah, I've forgotten the IntelliJ key combo for moving things around. So this test becomes the result of registration succeeded by itself and logged out, and that comes off the end, and that should pass. Yay. And this test becomes we're going to be anonymous, we're going to handle registration failed. So now the tests are identical, apart from the data that we're putting in, the events that are going to be that cause the state machine to transition, and the result that we expect. So, you know, in this case, I'm testing the type of the state machine at the end of the sequence. You know, if this was a real application, we might be testing some other side effect that's occurred. If you like to use some parameterized test framework, we could remove all of these tests and pass in here's what you start with, here's what you finish with. The parameterized test framework would generate the tests for you. This history approach lets you look at what might happen over a complicated set of events. So test something complex. We could say registration succeeds, then login succeeds, and then then logout succeeded, and then login failed, maybe 3 times, and then a registration failed event. And so maybe we have a bug report, and this is what happened to the user, and the system behaved unexpectedly, and they should be logged out, but actually they weren't. They became anonymous and everything was broken. So it lets you capture the story for the state machine. If we wanted to implement that a user is locked out after the login failed, what would that look like? So test user, if we keep the test names similar, so test failed login leaves user locked. Well, it doesn't, it leaves them logged out. A single test single failed login. So we have a registration succeeded, they're now logged out. We have a login failed, and they should still be logged out. Then that remains true for test 3 failed logins, leaves user logged out. 1, 2, 3. That should be true, and then we'll get our interesting test, and we'll say 4 failed logins, leaves user locked. And we've got to create a class, and the test will fail. They're logged out, they're not locked. If we look at our code, well, we've got a failed login count, which I can't spell, or 0. If login succeeded, they're going to log in. Otherwise, failed self.failed login count is going to increment, and they still won't do anything differently. And if self.failed login count is greater than 3, then we're going to return locked. Else, we're going to return self. Yeah. So now in this world, I can still introduce an error. I could increment the failed login count here, but I can't increment the failed login count when I'm anonymous. I can't when I'm logged in. I can't when I'm locked. So we've narrowed down the range, the number of lines of code where I can introduce a bug by misunderstanding this failed login count, which wasn't possible before this was a polymorphic state machine. It wasn't possible when we were mutating the state machine. I mean, we're still mutating it here, but we don't have to return self. We could return a new instance of logged out with a starting failed login count. So it doesn't have to have mutation in this case. Now we could say, well, we can test that we could test a successful login clears locked account. That shouldn't be how it works, but we can now test that and it'd be logged in this instance. That's, you know, that's utterly wrong. That test will fail. But I think, even given this isn't human language, I think you could sit with a sponsor or a stakeholder that doesn't understand code and say, if this was the sequence of things that happened and the person was logged in, is that right? Say, no, that's not right, you know. In fact, it shouldn't be possible to have a successful login when you're already locked out. That's probably as much state machine as it's worth writing. Hopefully that's clear for people. Maybe I could do a follow-up video. I'm tricking you into event sourcing a little bit here, which is my favorite thing in the world, but that's where you would have code like this, but you have more constraints around this sequence of events. I won't explain event sourcing now. Thank you. I hope that was useful and interesting.